All right, so today we're going to be doing a brief introduction to ab initio methods in computational chemistry. This is going to be one of your projects, one of your sort of more robust projects in this, one of the more robust projects, I guess, in your lab class. This will involve you going online, using the online tools and calculating the structures of some simple molecules. So this is kind of just to give you a brief overview so that you're more familiar with what's happening in the software, in the calculations. You won't actually need to do most of these sorts of calculations yourself. Thankfully, the software does most of it for us, but it's still good to be kind of aware of it and how the theory reconciled sort of computational difficulties with the realities of wave or quantum mechanics. So we'll mostly be talking about ab initio methods. So we won't really be talking about things like molecular dynamics or those sorts of techniques. We'll mostly be talking about ab initio techniques like density functional theory, DFT, Hartree-Fock, HF. We'll also be talking about some other theories like Molar-Plesset theory. But that'll be towards the end where we discuss about the little different approaches to solving what effectively is the Schrodinger equation for a particular molecule. So in case you were wondering why this might be important, so 2013, the Nobel Prize in Chemistry was awarded to these three men for their development of multi-scale models for complex chemical systems. So they sort of were pioneers in the use of computers to solve chemistry problems and computations. They also developed methods that made it more accessible to users like us. They're the ones that took the theories and created software packages that allow us to calculate complex phenomena and spectra about different molecules, but in a much more accessible manner without us needing to know all of the theory or to write our own computational codes. They allow us to calculate things like UV vis spectrum of a molecule, the FTIR spectrum. They enable us to find out heats of formation, bond lengths, bond angles, things which can be important in trying to rationalize organic chemistry reactions or trying to understand complex interactions between molecules. So computational chemistry is ubiquitous in chemistry, as experiments and data analysis often require some form of calculation. So whenever you're in the wet lab and you're doing an experiment, you're often calculating the number of moles of something that is required. You're weighing it out. All of those processes are a form of computational chemistry. We're computing those values. So it's fundamental, I guess, to experimental chemistry. But most computational chemistry that we'll be talking about today relies on quantum mechanics because molecular systems follow the laws of quantum mechanics. So hopefully that has been impressed on you through the lecture course as well. And well, whenever we were looking back at the UV vis theory, we also dealt with the particle in the box, and that was a rather simple quantum system. Quantum chemistry uses approximate solutions to the Schrodinger equation to explain chemistry. So the Schrodinger equation might have been introduced to you in your lecture class. We won't talk about it in huge detail here because it's not really the point of this session. But we will introduce sort of like the ways in which it is used in these sort of ab initio methods to calculate the structures, the electron interactions in particular molecules. So generally what we want to use is the time-dependent Schrodinger equation. This is a variation of the static Schrodinger equation, the one that you're probably more familiar with. Energy times the wave function is equal to the Hamiltonian times the wave function. This is probably what you're more familiar with. So E wave function is equal to H wave function. And we will get onto that later. But in reality, what we really want to be calculating is this one, the time-dependent Schrodinger equation. And the reason why we want to do that is because it tells us the evolution of our wave function, so the change in our wave function with the change in time. And so this would enable us to calculate the molecule or the particle as it proceeds through time and how the wave function changes, and we would get a dynamic picture of the evolution of the wave function as the molecule interacts with other things, as the molecule simply exists. We could see, like, we could calculate a very nice average picture of the different wave functions. So this is the time evolution of the system can be determined based on the wave function. So the wave function squared, as we saw back in the UV experiment, gives us the probability that n particles have a certain set of vector coordinates. So this wave function squared gives us the probability of where the n particles would be. These particles, generally speaking, for us will be electrons. And so this is just the probability of finding those electrons somewhere, these vector coordinates. So they're x, y, z coordinates. So we have here the ensemble has these particles from particle 1 to particle n, and it has coordinates x, y, z. So the vector coordinates here just means its position. And so the Hamiltonian then in this equation will give us information about how the wave function will change with time. So R is our ensemble of particles, and T is time. So the time-dependent Schrodinger equation, in theory, can predict the outcome of chemical reactions. So if, for example, we had this methylene cation and we reacted it with benzene, we could form this toluene, and we could actually, if we could actually calculate the time-dependent Schrodinger, we would be able to sort of view and predict the outcome of these chemical reactions. One of the issues with this is that it's just with current sort of computational power, it's not really possible. In this system, we would have 66 particles. We have 16 atomic nuclei and 50 electrons. So that would mean that we would have 198 coordinates to calculate for every sort of picosecond or even femtosecond of the system. We would have to calculate those positions of each one of those particles. And unfortunately, that's just beyond the computational power of what we have available. Maybe with the advances in like quantum computing and things like that, it may be possible in the next, I guess, 10 years, but right now it's not feasible for us. If we know that the wave function as it evolves through time, then the next step in the reaction can be determined by evaluating the Hamiltonian, giving the predicted rate of change as delta t, the time derivative. So that means that we can update our wave function to this one, which takes into account the changing time. So we start with time 0, so that's our initial position, and then we can have the wave function as it evolves over time. So as time changes, 1 second, 2 seconds, 3 seconds, 4 seconds, that sort of thing. And this could be done until completion, but it's impractical. So modifications have to be made. So it's impractical because, well, we just don't have the sort of computational power to even evaluate this system here. So what we do is, instead of using the time-dependent Schrodinger equation, we use the time-independent Schrodinger equation. And so this is, I guess, the most significant modification. There are other modifications which also come into play, but this is sort of the first approximation that we have to make, the first sort of put our hands up and say, okay, we're not quite able to calculate the real situation. And so in this, we hopefully are all familiar with the idea that psi is the wave function, E is the energy of the system, and H describes the potential and kinetic energy of the system. That's the Hamiltonian. It should be like a little hat. So this is the time-independent equation for static systems, but works appropriately for most systems. So it basically means that in our previous example over here, we would just have to calculate the molecules individually as they just stay in one position. So the nuclei would be effectively fixed. So the second modification then is to change the second approximation, you might see it called an approximation, is to change the wave function and split it up into two parts. One part describes the electrons around the nuclei, and the other part describes the nuclear motion. And you might say, well, why can we do this? Well, ultimately, it's because of the sort of relative speeds of the particles. In this case, we have lithium hydride, a rather simple system. It only has 4 electrons. But what we have are 2 nuclei, which are sort of almost infinitely massive compared to electrons. And as a result, they sort of just seem static compared to the motion of the electrons. So the electrons are generally moving much faster around the nuclei than the nuclei are themselves moving. And so, relatively speaking, we can say that, in fact, the nuclei are effectively fixed, whereas the electrons are going to be the only particles we really are considering as moving with any sort of great significance. You can sort of think about this in a way like the Earth is moving, but we don't really notice it, except for the change of time of day, but like you don't really feel it. So this is called the Born-Oppenheimer approximation. Is the name for this splitting of the wave function. And so then we can write the Schrodinger equations for each particle, for each electron in this case, where the wave function for the R, which is each one of these electrons, is equal to the Hamiltonian for the electrons times the wave function for each individual electron. So you'd have R1, R2, R3, and so on. So here we have our system at rest. So when considering a system, we assume coordinates for the nuclei, and then we solve based on that. So for example, we have this, we have a 4-particle system here. We'll have our wave function, which will be sort of the combination of all of our individual electrons. Each one will have a wave function. That was a terrible wave function. Each one will have its own x, y, z coordinates. So for example, this one could be our wave function 1. So it could have x1, x2, x3, or sorry, x1, y1, z1. Let's get rid of that. So we have x1, y1, z1, like that. This could be number 2. Then we have x2, y2, z2, and so on, all the way up to particle number n, which, for our n body system. So we have an n body system, which means we have, in this case, 4 electrons. Now remember, we have separated out our nuclear motion, so we're only considering electrons at this point. So for lithium hydride, there are 4 electrons, so the equation becomes something like this, up to where n is now 4, because our n body system is 4 electrons in this case. And so using this energy of the system, or using this, the energy of the system can be obtained from the Schrodinger equation, because remember we had the Schrodinger equation where the energy times the wave function is equal to the Hamiltonian times the wave function. So we can find the energy if we can know the psi r value. And so there are multiple solutions, but the one with the lowest energy, the ground state, is much lower in energy and the target of our calculations. So generally this is done by a semi-iterative process. There are obviously efficiencies that have been introduced that allow the more efficient calculation of the lowest energy. Generally, we're looking for the ground state. We have to move the atoms a little bit around to find that ground state so that the wave functions can interact with each other in a potentially more advantageous way. And so we have like, sort of like, you saw it in the FEIR, where we have like some sort of figure like this, especially for a 2-particle system, where we have the bond distance along the x-axis, where that's internuclear distance r, and then we have the energy E. So there is some minimum point somewhere at some distance. So we're trying to find this minimum energy point whenever the sort of the wave function gives us the lowest energy. And we do that, there are logarithms involved in the overall system, which allows the energy to be calculated for different positions. So only the simplest problems can be solved this way. We need more approximations. Yeah, so the issue here is that even as you start to increase the number of electrons, you start to increase the number of things that need to be moved, which means that you end up with ever increasing amounts of permutations or changes that can be made. And so it just becomes unwieldy. Like just you're doing calculation after calculation and you're not really getting anywhere. So what do? We make more approximations. And so this is where Hartree-Fock theory comes in. So this is kind of like the first, well, Hartree came up with a theory first, and then it was found that it didn't really satisfy much of quantum mechanics, but it was a start. And so it was then modified later by Fock, who was able to modify it to make it consistent with quantum theory. But it's sort of you also see it sometimes called self-consistent field theory. Sometimes you see that. Most of the time it's called HF theory or Hartree-Fock theory. But sort of the simplest. It's got some problems, but it's generally quite computationally efficient to calculate. Gives reasonable answers, although not exact answers. So the basic approximation here is that the electrons move independently from each other. So there's no like correlation effects. So sometimes called molecular orbital approximation, where this wave function for particle 1 to up to n is approximately equal to the product of each wave function. If we have a wave function for electron 1, if we have a wave function for electron 2, if we get the product of those, that's approximately equal to the total wave function for the system. And then the orbitals are orthogonal to each other. So that's something that will have come up hopefully in your lecture as well, this idea that the orbitals cannot be identical, they have to be orthogonal to each other. And so this equation needs some modification. So that's our equation that we had from the previous one, so we haven't modified it yet. So the wave function R1, so this part becomes chi1 R1 omega. This is to account for the spin component. So R1 omega can then be written as X. So this is the coordinate of a particular electron in our cases is going to be called Xi, where I is the number. So X1, X2, X3, so on. Then we have chi is our wave function. So the second approximation is that each electron is identical. So thus each combination is anti-symmetric to coordinate swapping. So what does that mean? It basically means that we have this wave function, which is, for particle 1, 2, 3, and 4, or electron 1, 2, 3, and 4. And it can, if we change the position of, say, for example, particles 2 and 3, we swap them, the wave function must change because quantum theory cannot tell particles apart. It can tell us where the particle is, but it cannot tell us which particle it is. So if we were to swap these two particles, X2 and X3, swap their position basically, then we would run into a problem where they are identical. And we know that from the Pauli exclusion principle, no two electrons can have identical quantum numbers. They cannot be identical. And so that's not allowed. So the way that it has to be is that we have to have what are called linear combinations of these electron positions and wave functions, such that we end up satisfying this anti-symmetric requirement. And so we end up with, like, say, for example, we take a simpler system where we have chi1, we just have a 2-electron system, and x1. If we then have chi2, and so that's electron 1 and electron 2 in position 1 and 2, that we cannot have a system where if we change the position of electron 1 to be x2, it cannot be that this system is equal to each other. Like, we've changed the position of the electrons. They have to, this is not possible. They cannot be equal to each other. Because if they are, then they're not satisfying the Pauli exclusion principle, which means that we have to form them as a linear combination of each other. And so what would happen is the wave function is going to be equal to the normalization factor. So this is just to make sure that everything is normalized. It has to be a linear combination of these two. I should probably just type this out. It's time consuming to write equations. So this would be how, I mean, you don't need to do these calculations yourself. This is what is happening under the hood of the software. X2 okay, something like that. So that's a linear combination then of the two potential combinations. That can then be rewritten as a matrix, which happens to be a specific version of a Slater determinant, which is going to allow us to basically solve this equation for our individual system. It's going to allow us to take into account all of the electrons that we have. It's going to allow us to make sure that they're not identical to each other, but also to make sure that they can occupy different positions. And so that's where this idea of the Slater determinant or the Slater matrix comes in. So we can express the n-body electronic wave function as a single Slater determinant, which satisfies the Pauli exclusion principle. So you can see here that if we have n bodies, so we have n electrons, so n, x1, x2, and so on, each one of these, electrons, or each wave function, can occupy all of the available positions. So if there are n bodies, that means there are going to be n positions. So n is equal to 2, 3, 4, whatever. So if there are going to be 5 particles, for example, that would mean that there would have to be 5 different potential positions for the wave function, which would mean that each individual electron wave function can exist in up to 5 different positions. So that's why we formed this matrix of all those possible permutations or possibilities, but we have to normalize it always by the number of particles in the system. Otherwise, we would end up with an answer which is basically has a number value for every possible combination, which would be the number of particles to the power of the number of particles. So it would just be way too big. So we have to normalize this matrix so that we only have the 5 particles that we started with. So minimizing the energy of the Slater determinant optimizes the orbitals. So we start off with some sort of approximate guess for our wave function, usually based on some sort of chemical intuition. How we do this as an individual user is to create the molecular structure using some structure builder like I don't know, Avogadro or VMD or PyMol or something. And we draw out the molecule, we put like a carbon, we put hydrogens around that carbon, and then the software can use those XYZ coordinates for each of the nuclei, like the hydrogen nuclei and the carbon nuclei, and it can then generate wave functions of sufficient accuracy that the energy can be calculated for that system, and then usually that energy is very high, and then changes can be made to the positions of the wave functions so that the energy gets lower, and then eventually we end up with that lowest energy in the sort of the Leonard-Jones type curve. We end up with this internuclear distance R, this is the energy E. We end up eventually moving towards the minimum down here. So how does the Hartree-Fock system work in practice? So initial guess of the system orbitals are made. That's made from the information that we give. The software doesn't think for us. It calculates for us. But we have to create an input which is chemically reasonable, because the software will use the rules of quantum mechanics along with these approximations that we've made in order to calculate the various properties that we want to know. So an initial guess of the system orbitals are made. The Slater determinant is then evaluated using this equation here, where the energy, the approximate energy, is equal to the integral over all of the possible particles as such. And so after evaluation of the orbitals, changes are made until the energy is minimized. And once we get to that minimum energy, then assuming that it's chemically significant or chemically consistent, we accept that answer and we say, okay, well, we've reached the minimum energy now. So this must be, and we've checked that this is really the minimum energy. Then we say, okay, this system has been solved. Now is the time to try and calculate the other properties like the UV-Vis spectrum, the FTIR spectrum, maybe heats of formation, and so on. But this process involves probably too many steps, and how to vary the orbitals is non-trivial. So, like, how do we change those wave functions? How does that happen? Like, what is the process which governs that? It's not an easy problem to solve. I mean, there are many possible ways that you can move the wave functions around, but there has to be one way which is used at the end of the day. And so the way that is sort of done is well, thankfully by the software. But to do it like one by one would involve too many steps. So this is kind of like, I took this from Wikipedia. This is kind of the step-by-step way of this, the way that the software sort of calculates the Hartree-Fock energy. So we input 3D coordinates of the atomic nuclei. So in the case of lithium hydride earlier, put like lithium and hydride together like this, or if it's methane, we'd like put in coordinates for each one of the hydrogen and carbon atoms. So we would draw these out then using something like Avogadro, VMD, whatever you choose to use. The initial JMOL even. The initial guess is then made based on the molecular orbitals. So this is where our one electron vectors come in. You remember we separated everything out as a product of all of the available electrons or wave functions. Then we formulate this the Slater determinant matrix. Then it calculates through that, basically. It diagonalizes. It basically calculates the answer to the matrix. And then it checks if the SCF has converged. So has the energy got to a minimum based on the criteria that we give it, because it keeps solving this matrix until such times as it has reached a solution which has a minimum energy. So it continues in this process of changing the matrix, or changing the matrix formation. So basically moving the atoms a little bit around, and then or moving the wave functions depending on what kind of calculation you're doing. And then it calculates that wave function again, or the matrix of that wave function, and then it checks if the convergence has happened according to our criteria. And if it has happened, then it ends and it calculates the properties, like heat of formation, the energies of the different orbitals, and so on. So the LCO approximation, so this is the linear combination of atomic orbitals approximation. So this is kind of fundamental to molecular orbital theory in organic chemistry, and also you'll talk about it, I'm sure, a lot in the quantum chemistry lecture. So Hartree-Fock HF, so that's what this HF stands for. It's not hydrogen fluoride. Right, wave functions are written in terms of one electron molecular orbitals, MOs. So these molecular orbitals can be written as linear combinations of atomic orbitals. So this is how we get on to molecular orbitals. So we have here our wave function for this particle number 1 is equal to the sum of all of the atomic orbitals, where chi mu are the atomic orbitals or basis functions. So basis functions will come into this later. Basically a mathematical way of describing the atomic orbital. And then C mu I are the molecular orbital coefficients, which determine sort of like the expression of that molecular orbital, or like the contribution of that molecular orbital to the overall system. And so that means then that the energy of the Hartree-Fock energy can then be written as this, where the energy HF is equal to the sum of the Hamiltonian for each particle plus a half over the sum of the two electron exchange term. And then this is the Coulomb repulsion, and this is the exchange term of the electronic coordinates. So HI, the one electron term arising from the kinetic energy of electrons and nuclear attraction energy. J, Ij, so I is one particle, J is the other. So in this case, electrons, two electron terms associated with the Coulomb repulsion between electrons, and Kij is the two electron terms associated with exchange of electron coordinates. So this one accounts for two electrons repelling each other, and this one accounts for two electrons being associated with each other and being able to change their electronic coordinates. Because remember, even though we can, whenever we're doing our electronic configurations, we can assign electrons to orbitals. Unfortunately, quantum theory cannot tell us which particle is which. And so we have to assume, and at least in Hartree-Fock, we have to assume that we're able to just move these electrons around. They can occupy any position that's available in any wave function. And so it's part of the computational cost, I guess. Like we have to say, well, this electron can go here in this wave function, and then the electron that was in that wave function can go into a different wave function. And so eventually, you know, the more electrons you have, the more wave functions you have, the more things you have to calculate. So here we have, for example, the molecular orbitals for HH, H2. So this is for a sigma bond. So the sigma bond is where most of the electron density is between the two nuclei along the internuclear axis up here. So this is the bonding sigma, and then this is the anti-bonding sigma up here. So we can have then two combinations of our atomic orbitals. So we can have the bonding and we can have the anti-bonding. We normalize it here based on the number of particles, which is 2 because we have 2 electrons. Then we have for spin up and spin down. So the 1s spin up, 1s spin down. So we've got, remember, electrons spin up, spin down. It's a linear combination. So for the bonding orbital, they combine as a sum because there's no node, but then as a anti-bonding orbital, there is a node here, and you subtract one from the other. And so for H2, the molecular orbital coefficients, this C mu I is equal to plus or minus a half. So here it is. Those are the molecular orbital coefficients for that H2 molecule. So this is a very simple case, but it's basically what you would do for other systems as well. Variational principle. So we're coming to sort of the end of talking about the basics of Hartree-Fock and what's going on in that process. So here we have the wave function for the whole system. It's a sum of all of the different wave functions of the particles. This case, in our cases, it's typically electrons. This is the Hamiltonian for those individual particles. And we can then, we can then substitute this first equation into the Hamiltonian equation, and then we can get a value for the Hamiltonian based on the individual atomic orbitals. So similar expressions in terms of C mu I can also be written for Jij and Kij. Thus, solving for the coefficient values is needed to calculate the HF energy because it exists in basically all of the terms. So we need to know this C mu I is the measure of how much that molecular orbital contributes to the overall system. And so that means that we need to know what it is, because if we misinterpret this, we might have an over expression of a particular molecular orbital in the system, and that would lead us to an incorrect value. And we would think that we have the right value, but in fact, we do not. So this coefficient needs to be calculated. Thankfully, all of this is done by the software. I'm just trying to tell you about it. So the molecular orbital coefficient here can be determined using the variational theorem, which makes use of this. So the energy, the variational theorem is the energy determined from any approximate wave function will always be greater than the energy for the exact wave function. It's very difficult to determine the exact wave function. Thus, the energy of the exact wave function serves as the lower bound on the calculated energy. The molecular orbital coefficients can be continuously adjusted until the total energy is minimized. So we constantly move these around a little bit, or we combine them in slightly different ways, because even though every electron can fit in, or can theoretically be in any particular wave function, any wave function can be in any particular position. What ultimately happens is that there is one combination which has a lower energy than the others, and it is that which we are looking for. It is that which we are working towards continuously until such times as we've reached that minimum in the Lennard-Jones. This part here. Okay, I'm going to take a drink of water. That was a Hartree-Fock theory in a nutshell. That is the simplest theory. Okay, so this is a quote ascribed to Carl Irikura, a computational chemist. So anyone can do calculations nowadays. So like anyone can use a black box. They can use various like turbomole, or they can use games, or you can use Gaussian, Orca. There's tons of softwares out there, or software choices. So, but anyone can also operate a scalpel. That does not mean all our medical problems are solved. So, it's the idea here is that many people spend a long time trying to study this. So I probably shouldn't go into an operating theater and attempt to do even the most basic of surgical procedures, because I have no training. But I can hold a scalpel. I can do that. And so what he was basically saying was that we need to understand a little bit about the theory before we use it, because if we don't, we're liable to sort of just get the wrong answer, or think that we have the right answer and then turns out we don't. So yeah, basically that. Doesn't mean don't use it, just it's better to have at least thought a little bit about the theory. So conducting a computational project. So this is moving more towards the practical aspects of what will be happening in your project. Actually, if you follow what's on the PDF that you'll be given, you should be able to do it no problem. The following questions should be answered. So what do we want to know? Like whenever we shouldn't just be going and doing a calculation and thinking, I'll just calculate the optimized structure and orbital wave functions of HF, hydrogen fluoride in this case. But why do we need to know that? What is it that we're trying to find? Because we need to know what we want to get out before we can start. Do we want to know the FTIR? Do we want the UV vis? Why do we want to know the UV vis? Maybe we want to compare it to a UV vis spectrum we already have. And so that would enable us to interpret the UV vis spectrum we have. Or it can also help us to interpret FTIR spectra that we have. We get all these lines in FTIR, but we don't really know what each line corresponds to. But if we have a well-resolved structure, then or computational structure, then we can calculate as well as that the FTIR peaks, and then we can assign those peaks in our research. And instead of sort of being like, well, I have this FTIR, but I don't know what anything in it means, we have this opportunity then to assign those peaks and say, well, if we change the temperature of our system, we can see that the peak that corresponds to the CH asymmetric stretch weakens, and what does that mean? Something like that. How accurate does the prediction need to be? Do we need sort of like bulletproof prediction accuracies? Does it need to be super duper accurate, or will a rough calculation do? Is it okay to throw in a few extra approximations, because that will save us time? Whenever we talk about computational projects being expensive, what we mean is that it takes a long time, but it can also take 10 minutes. It just depends what level of accuracy you need. And how much time can be devoted to the problem. If you have a full, if you're doing a full PhD or something, then you have a lot more time on your hands than if you are doing a project for a lab class. So obviously, like that's the you don't have as much time on your plate to be able to devote to this. So it means that the calculations that we give you are relatively straightforward. It shouldn't take more than an hour or so of your time. And then the next thing is what approximations are being made. Like, if I'm only calculating it to this level of theory, is it appropriate that I also calculate the FTIR spectrum? Or would it be better to use a different method of calculating the wave functions? And things like that. These 4 questions are kind of like the first 4 that I thought of whenever I was trying to figure out or trying to go through my head what steps I would be taking. And so the answers to these questions will determine the type of calculation, model, and basis set used. So types of calculations. So there are 3 basic types of calculations. From these calculations, other information can be determined. So for example, here we have the atomic model of the buckyball, which is the C60. So this is this geodesic shape. So single point energy, this predicts stability or reaction mechanisms. It doesn't attempt to move the atoms around at all. It just literally takes the structure that you've given it, and then it predicts the stability. So this is the kind of method that we would use if we want to know about transition states, or if we want to know like a reaction, if there's a hydride transfer in the reaction, we put the hydrogen between the 2 molecules or whatever, and then we see what the energy there is, and then we try to determine if that's an appropriate step in a theoretical reaction mechanism. And so these single point SPEs are very useful if you're doing a mechanistic study. Geometry optimization, so this is you're predicting the shape. So maybe you want to know how 2 water molecules interact with each other. Maybe that's something you want to know. You want to know what the angle is between them. Do they interact linearly, or is there like a twist, or that sort of thing. Like, does because of the formation of a hydrogen bond, does one of the bond lengths change? That sort of thing. Frequency then are to predict spectra. So we can predict FTIR, UV-Vis that I've talked about. Even NMR can be predicted. You can also predict different thermodynamic properties. All of those things can be predicted using these ab initio techniques. And so that's a powerful way to sort of confirm that our optimized geometry is correct. So for example, say we had an FTIR spectrum, and then we had an optimized geometry and calculated the FTIR, like we had an experimental FTIR spectrum, and then we went ahead and we calculated the structure of the molecule, say we had ethanol or something. And then from that optimized geometry, we then calculated the FTIR of the ethanol. Then we could compare that to the experimental spectra that we got, and we can say, does this match up? Like, is this a reasonable geometry? Is this what the geometry is likely to be? And it can give us that sort of additional clarity, that additional sort of that the calculation has a basis in experimental observation. Because ultimately, like in all of this, we have to justify our conclusions. Computational model. So a model is a system of equations or computations used to determine the energetics of a molecule. So that's various wave function energies. So different models use different approximations, or sometimes you'll see it called levels of theory, to produce different varying levels of accuracy. So the HF, the Hartree-Fock theory that we use, is a very simple theory compared to some of the others. So it lacks a little bit of accuracy in certain aspects. So some aspects is actually very good. But for other things, it's maybe not the best. Like, for example, if you calculate an FTIR spectra based on your Hartree-Fock calculation, you will expect to see some differences between the experimental and the calculated, because the Hartree-Fock doesn't really consider how electrons interact with each other that well. It does make an attempt, but it's not perfect. So there's always this trade-off between accuracy and computational time. If you want to get, like, for example, there's always like because like we can't actually get the exact energy most of the time in this calculation, there is always like a little bit of discrepancy in our what do you call this? In our output between the real system and the calculated system. And typically, this only really comes into play whenever we're dealing with calculations of spectra. So one of the issues with the calculation of FTIR spectra using HF or DFT or whatever is that it typically only views a chemical bond, like for example, a carbon-hydrogen bond. Typically, the standard way is just as a harmonic bond, like the sort of the spring system. And we've already talked about in the FTIR session that in fact vibrations are not harmonic, they're in fact anharmonic. But this anharmonicity has a computational cost, and that cost is time. And so typically this is very accurate. To calculate it using an anharmonicity sort of what do you call this? Correction will lead to a very accurate value for that stretch frequency. But it'll take a very, very long time for anything other than the simplest systems. So it's typically only done if you have the time or you have the computing power. And so there are two main types of models, those that use Schrodinger's equations or simplifications of it, and those that do not. So types of models. So ab initio, this uses Schrodinger's equation, but with approximations. So Hartree-Fock falls under this category. And semi-empirical uses experimental parameters and extensive simplifications of Schrodinger's equation. So that's like MP2. And molecular mechanics, which does not use Schrodinger's equation at all. So this is sort of going into your molecular dynamics, which uses sort of more classical dynamics to understand the movement of the particles. It typically considers atoms and molecules as one whole particle instead of separating them into electrons and nuclei. But this simplification does have huge value because it means that you can have many, many more particles in your system. So if instead of having, a hydrogen has a nucleus and one electron, that's two particles already. If you do it in molecular mechanics, you only have one particle for the hydrogen atom. And so what ends up happening is you've halved the number of calculations you need to do. And so if you do that for carbon as well, carbon has what? 12 electrons, it's got 6 electrons, it's got 6 protons and 6 neutrons in its nucleus. So that's what? So the nucleus plus 6, that's 7 particles. If you just count carbon as carbon, then you've reduced that by 7. So you've only got 1 instead of 7. So there's a huge value in that, but it doesn't tell you anything about orbital occupancy. It doesn't tell you anything about the shapes of the wave functions, those sorts of things. So there are trade-offs. Depends what you want to know. Ab initio. So ab initio is translated from Latin, means from first principles. So the first principles here is that we're using quantum mechanics. So this refers to the fact that no experimental data is used and computations are based purely on the laws of quantum mechanics. So we have different levels of ab initio calculations. So we have the Hartree-Fock, which we talked about. This is the simplest ab initio calculation. The major disadvantage here is that Hartree-Fock calculations is that the electron correlation is not taken into consideration. So that means that there are going to be some inaccuracies. But because it doesn't take into consideration the electron correlation, it is very fast. And it gives a reasonable answer. Molar-Placid perturbation theory then, so this is commonly called MP. This is the cheapest method to include electron correlation and is actually really valuable if electron correlation is a big thing in your system. It typically is for like things that are hydrogen bonded or things that have dipole moments. It's important to consider those. So usually there are different levels of molar-Placid theory. There's MP1, MP2, MP3, MP4, whereas the number gets larger, the accuracy improves, but as accuracy increases, so too does time. And then density functional theory, which is quite different from the other two in that it doesn't really consider the wave function, instead looks at something called electron density. And then configuration interaction. This is the most expensive. This is very accurate, but again, it's very expensive to do computation. But it can really tell you a lot about the occupancies of the different wave functions. It can tell you a lot about their shapes, a lot about their energies. It can tell you about different excited states very easily. Things that, like, for example, Hartree-Fock really cannot do or struggles with mightily. Approximations used in some ab initio calculations. So central field approximations integrates the electron-electron repulsion term, giving an average effect instead of explicit energy. So linear combinations of atomic orbitals, talk about those. Also, hopefully have encountered those in inorganic chemistry and in the lecture. So these are linear combinations of atomic orbitals is used to describe the wave function. And these functions are then combined into a determinant, this matrix that we looked at. This allows the Slater matrix, this allows the equation to show that an electron was put in an orbital, but the electron cannot be specified. Like, we cannot say which electron is in which orbital. All we can say is that there is an electron there. Density functional theory. So this is considered an ab initio method, but is different from other ab initio methods because the wave function is not used to describe a molecule. Instead, the electron density is used. So this happens to make it a lot cheaper computationally. It's a lot easier to calculate complex systems. 3 types of DFT exist. We have LDA, local density approximations, is the fastest method, gives the less accurate geometry, but provides good band structure. So this is important in like alloys of metals or different semiconductors. Band structures are important there. Gradient corrected, this gives more accurate geometries. And then hybrids, which is the general sort of combination of DFT and Hartree-Fock methods, give more accurate geometry. So whenever we combine a certain amount of Hartree-Fock exchange energy, then we improve the quality of the DFT. So because the DFT is using electron density, it doesn't consider electron exchange in any way. Of course, Hartree-Fock also doesn't include electron correlation, but at least by including some of the exchange energy, we can provide a better picture of the DFT. And so usually the methods that you'll be using in the project will be these sort of hybrid models. So these types of calculations are fast becoming the most relied upon calculations for nanotube and fullerene systems, also for just general systems. DFT methods take less computational time than Hartree-Fock calculations and are considered more accurate. So this 15-0 short zigzag carbon nanotube, so this one, was calculated with 2 different models, the Hartree-Fock and the DFT. And you can see the energies here are quite similar. The energy is somewhat lower for DFT than it is for Hartree-Fock, but it's minimal. Semiempirical methods use experimental data to parameterize equations. So like the ab initio methods, a Hamiltonian and wave function are used. Much of the equation is approximated or eliminated. So the Hartree-Fock is quite simple because it doesn't take into consideration electron correlation, so how electrons influence each other. But it will improve our sort of semi-empirical systems that just try to take experimental values and parameterize the calculation based on those. So it's less accurate than ab initio methods, but also much faster. So equations are parameterized to reproduce specific results, usually the geometry and heat of formation, but these methods can be used to find other data. So like you can use X-ray spectroscopy to find geometries of different chemical compounds, and you can calculate heats of formation, that's sort of like your Born-Haber cycle and stuff like that, reasonably easily. Like there's usually a lot of tabulated data, and so you can find the heat of formation of most things experimentally. You can then feed those values in, most of the time the calculation and software finds those values for you, at least the heat of formation ones. And then it can use that to try and calculate the system, and then it can be used to find other data. So what it will do is it will look at the experimental heat of formation and experimental geometry, for example, and say, okay, the heat of formation is still not correct. It's not the experimental value. It's not close to experimental value yet. So we have to move things around. We have to try different combinations until such times as the heat of formation geometry of the calculated system and the experimental system converge and are consistent with each other. Molecular modeling. So this is simplest type of calculation, but it's typically only used for large systems. Does not use any quantum mechanics, instead uses parameters derived from experimental or ab initio data. So actually what some systems do is they, or some molecules and things, the experimental data maybe is lacking or doesn't exist. So what you can do is you can calculate it to a reasonably good standard using ab initio techniques like our DFT or Muller-Plesset theory or our Hartree-Fock or whatever. And then from that, we get parameters for like the charges of a particular atom, the partial charges in a molecule, the size of the nucleus and stuff like that. And that can be used then to perform these molecular modeling, what do you call this? Molecular modeling experiments and calculations. The energies obtained from molecular mechanics do not have any physical meaning, but instead describe the difference between varying conformations. So for example, type of isomer, like maybe of cis-trans isomerism or whatever. And so you can sort of tell how, like if say you have a mixture of alkenes, whatever alkenes they are, you can like find the relative distribution of what do you call this? Cis and trans isomers, stuff like that. You can also find like, okay, so I have this polar molecule. So what is, how do the molecules arrange themselves with each other? You know, do they form extended hydrogen bond networks? Do they all align in a nice little line? Or, you know, like what kind of structure is there? Like, and that can tell us very important information to try and rationalize experimental results of other people or even our own experimental results so that we can understand the chemistry that we're doing. And that's one of the fundamental importances of this type of work, is that it's okay to have these experimental results, but oftentimes we want to know why something is the way it is. Often we can give a good sort of postulate answer based on our understanding of chemistry, but sometimes it's nice to have additional sort of evidence. Okay, so sometimes in the project, you'll also come across something called a basis set. So the basis set is the way of describing the wave functions, because they are, as you know from wave mechanics, wave functions can be described mathematically by an equation. So a basis set is a group of mathematical functions used to describe the shape of the orbitals in a molecule. So, you know, the standing waves. So each basis set is a different group of constants used in the wave function of the Schrodinger equation. Accuracy of a calculation is dependent on both the model and the type of basis set applied to it. And there's a trade-off between accuracy and time. Larger basis sets will describe the orbitals more accurately, but take longer time to achieve. General expression for the basis function is this, where the n is the normalization constant, e is the mathematical letter e. I can't remember what that's called. To the power of, or I can't remember. And then to the power of this product of r, the radius of the basis function, times alpha, which is the orbital exponent. So generally, as we increase the size of the basis set, what happens is we take into consideration more of the excited state orbitals. So for example, we include, so hydrogen obviously has a 1s orbital. A very simple basis set would only include the 1s orbital, so it could not enter in, like it couldn't form linear combinations of its higher orbitals with other molecules. More extensive basis sets might include the 1s, the 2s and 2p orbitals for hydrogen. Even more, could even include up to the d, 3d, and even up to the 4f orbitals. And just by including more orbitals, we can improve the accuracy, because the more orbitals we have available in our calculation, the more opportunity we have for orbital overlap. And that means we can try out different combinations, which probably means that we can reach a more accurate answer. But sometimes it's just not necessary. Like sometimes there's no real reason to use such an accurate basis set, because it's not going to tell us any additional information. It's not going to really play into improved accuracy. And so that's just kind of where personal experience comes into play. So examples of basis sets. So this STO3G basis set is the simplest basis set and uses a minimal number of functions to describe each atom in the molecule. So the hydrogen atom here is described by one function, the 1s, while the carbon is described by 5 functions, the 1s, the 2s, the 2px, 2py, and 2pz. So this is what I'm talking about whenever we have a very simple basis set. Basically means that the hydrogen only has one orbital available to it, so it cannot be excited in any way. Then sometimes we have what are called split valence basis sets. So these use 2 functions to describe different sizes of the same orbitals. So a split valence basis set for hydrogen would be described by 2 functions, while carbon would be described by 10 functions. Polarized basis sets improve the accuracy by allowing the shape of orbitals to change by adding orbitals beyond that which is necessary for an atom. So remember, we can combine orbitals linearly. So if we needed to change the shape, it's not really so applicable to hydrogen, but if we needed to change the shape of the carbon orbital, like for example, we needed to build a tetrahedral shape, by having more orbitals available to us, we can combine those orbitals to create electron density along the carbon-hydrogen bond, which would, allow us to potentially have a better minimization of energy. So, for example, one that is commonly used, I'm not quite sure which orbitals I recommended you use, or which basis sets I recommended you use in the project, but anyway, it'll be there. So 631G D, so it's diffuse or adds the D orbital, also known as 6-31G star, where the star means that we've added a D function to the carbon atoms. So these are slight modifications of the basis sets. Diffuse functions, so these add additional functions with large spatial extent. So this accounts for, like for example, your induced dipole moments, or very large atoms having this polarization of their electron density, things like that. That's where the diffuse functions come into play. So allow for accurate modeling of systems with weakly bound electrons, such as anions or excited states. 6-3 plus G has diffuse functions on heavy atoms. 6-31 plus G has diffuse functions on hydrogen atoms as well. So this plus indicates that we're adding extra functions or wave functions or mathematical equations, basically, that allow us to describe sort of a simulated orbital which can account for these additional sizes of things like anions and excited states. Mixing of functions and larger basis sets can be built up from these components, so we can add extra D and F orbitals and so on. So this is where we add D and F orbitals to hydrogen and add, P and D orbitals to hydrogen, add D and F orbitals to things like carbon. So some basis sets work better for a certain type of calculations, so HF and DFT calculations, correlated calculations. And some are designed for use in other things. So the number of basis set functions in modeling a molecule will determine the cost of the calculation. So the more equations you add, the more equations have to be solved, the more time it takes. Even if you're writing something out on a page, the more equations you write on the page, the longer it takes. Same for a computer, although the computer is really quite good at doing these calculations. So here's a kind of a brief description and comparison of the number of functions for different atoms. So if we have the STO3G, that's a minimal basis set. So it has 1 function for hydrogen, 5 for carbon, 7 for water. And then for, so basically for every atom, we have this many functions. So in benzene, we have 6 carbons. That's 6 times 5 is 30. And then 6 times 1 is 6. So 30 plus 6 is 36. Oxygen also has 5 functions. This is because it has 5 occupied orbitals. So 1s, 2s, and then the 3 2px, 2py, and 2pz. Oh, that was a little bit big. So there's 1, 2, 3, 4, 5 orbitals. So that's the minimum we could have. Like if we don't have at least 5 orbitals, we can't describe all of the electrons in carbon or hydrogen or carbon or oxygen. Then if we look at the 321G, we have a double split valence. So we're now introducing the idea that we can have another orbital on those, what do you call this? On those valence orbitals. So hydrogen has 1 valence orbital, the 1s, so now it can have 2. So that's sort of kind of like the bonding and anti-bonding. And then we have here in carbon, we have 5 for the minimal, but we don't double 5 to 10. We instead have 9 because it's only the valence orbitals which are doubled. So that's the 4 valence orbitals, the 2s, 2p, x, y, and z. So that's 4 times 2 is 8 plus the 1, that's the 1s, the core orbital. So that becomes 9 and so on. You can go through that and use the information I gave you on the previous slides if you want to kind of talk through that. So 6-3-1GD, so double split valence with polarization. 6-3-1GDP, so has the same, but now has p functions on the hydrogen. So now we have the 2s and 2p. Now we have this one, 6-3-1-1 plus GDP, so triple split valence with polarization, p functions on hydrogen and diffuse functions on heavy atoms. So this basically increases by a lot the number of mathematical equations which describe that system, which in turn means that we have many more equations to solve, many more equations to change, because each one of these functions represents a wave function where an electron can exist. And so in order to find the minimum energy, we need to solve these multiple times. So the more you increase the accuracy, the more time it will take. So accuracy of calculation. So accuracy of calculation can be affected by the choice of basis set. Accuracy of a computed property is sensitive to the quality of the basis set. So here is a calculation. I think this is for the hydrogen. I'm not quite sure I can't remember what bond this is for, but it's basically a comparison of how the bond length changes and how the energy of that bond changes. That's the dissociation energy with different basis sets compared to the experimental. So you can see here with a rather simple basis set, there is a significant difference between the bond length computed 0.9337 and that experimentally determined bond length here, 0.917. But if we improve the accuracy of the calculation, we can get a better bond length. But just because we've got a better bond length doesn't mean we've actually got a better representation of the dissociation energy. You can see here that the 6-311GD, where we have d orbitals on the carbon atoms, provides a very nice bond length. It's very similar to the experimental, but the dissociation energy is not accurate. But presumably this means it's involving hydrogen of some respect, maybe a carbon hydrogen bond, I'm not quite sure. But if we then add the diffuse functions, so p orbitals to the hydrogen, we now have a dissociation energy which quite closely matches that of the experimental value. And again, this bond length is, well, depending if we take it to 3 significant figures, is exactly the same as the experimental value. And so you can see that as we increase the number of functions in our basis set, we also improved the accuracy of our calculation. And so this is one of the reasons why we might want to use the basis set. But of course, if you consider like how long this calculation took compared to this calculation will take a lot longer. Maybe, I don't know, it's kind of exponential increase in time, so it's hard to estimate, but probably at least 5 to 10 times longer. So in summary then, Schrodinger's equation is the basis of computational chemistry, as it is very important in quantum or wave mechanics. If it could be solved, all electron information from a molecule would be known. Since Schrodinger's equation cannot be completely solved for molecules with more than a few atoms, computers are used to solve approximations of the equation. Level of accuracy and computational time of a simulation is dependent on the model and basis set used. And that's that. These are my references. This is where I got a lot of this from. Some of it is based on Dr. De Jesus' lecture a few years ago. This textbook is very nice. If you have like additional interest in this topic, beyond what you have to do in the project here, I recommend this textbook. Goes into a lot more depth than I did. It also has more time to introduce it. So yeah, that was that. I don't know if you have any questions or not.